We're ready to begin the final video over section 6.6 on surface integrals. We started by computing the surface area of a surface, where a surface was a sort of two-dimensional object that nonetheless existed in three-dimensional space. We could think of it sort of like, well, a sheet flapping in the wind. At any given point, it's two-dimensional, has length and width, but no depth or height to it, and yet it exists in three-dimensional space. After learning how to find surface area and using it to find the surface area cut out of a bicylinder producing a Steinmetz solid, we took a look at surface integrals of scalar valued functions. We used that to find the mass of a surface given the density function. In this video, we want to focus our attention on a surface integral again, but this time on a vector field. We have three learning objectives left to complete. Our learning objectives are to explain the meaning of an oriented surface and give examples. Then we want to describe the surface integral on a vector field and use the surface integrals on vector fields to solve application problems. Let's go ahead and get started. When we studied line integrals, we learned that there were two types of line integrals: scalar line integrals and vector line integrals. Scalar line integrals did not require there to be any kind of orientation along the curve, but vector line integrals did. We're going to see a very similar situation here with surface integrals. When we computed a surface integral of a scalar valued function, there was no particular orientation to the surface. But now that we have a vector field involved, which definitely has a flow in a particular direction, we're going to find that we need to orient our surface. So this is very similar to what we saw with line integrals. There are two basic types. One type that does not require orientation, the scalar line integral, and the surface integral of a scalar valued function, and one that does require orientation. A vector line integral, which requires the curve to be oriented, we tend to go counterclockwise in the positive direction, and a surface integral on a vector field, which will likewise require orientation for the surface. Unlike what we saw, however, in a vector line integral, where we could compute the vector line integral for any curve, not all surfaces can be oriented. There is an example of a surface which cannot be oriented, which is known as a Mobius strip, and we'll take a look at these in more detail later on. Now, we're going to have to come up with an acceptable orientation for the positive direction of a surface. Just as we arbitrarily chose counterclockwise to be the positive orientation of a curve, we're going to choose upward or outward to be the positive orientation of a surface. When we say upward, we generally mean pointing above the XY plane, and downward would be pointing below the XY plane, though not necessarily directly above or directly below. Let's define what we mean by an orientable surface. Let's suppose that on our surface, we can choose a unit normal vector at every point on the surface, so that the normal vector varies continuously over the surface. If it varies continuously, then we say that the surface is orientable. Now, the unit normal vector at each point will give us the orientation of the surface, where we think of the normal vector as describing the direction of the flow. If we think of the vector field as describing the flow of water in a flood, then the side of the surface that we're flowing away from is the positive side, since it's a positive thing for the water to go away and us not to drown. If we think about the side that the water is flowing towards, then the water is coming in, we might drown, which is a negative thing. We can also think of the orientation of the surface as separating it into an upward and a downward. In this particular image here, you can see that two normal vectors, n1 and n2, are pointing in a general upward direction. This, however, is an example of what we would call a closed surface. And when we think of a closed surface, we're thinking of a surface that is the boundary of some solid. And we can call this region E. When we have a closed surface, then we don't just think in terms of upward and downward. Instead, we think of outward and inward. Out of the closed surface is the positive orientation, which means that even in this case, if I point down in the negative K direction, I'm nonetheless pointing out of the sphere, and that makes it the positive orientation. The negative orientation would point in towards the center of the sphere. So depending on what type of surface you have, whether it's closed or not closed, you will have to define the orientation differently. Let's talk about a non-orientable surface now. A non-orientable surface is one for which there is no clear inner or outer side or up or down side. So what does that mean? Essentially, you can't tell the difference between the inside and the outside, or the top and the bottom side. So let's think about a Mobius strip. If you take a long piece of rectangular paper, give it a half a twist with one hand, and then tape the ends together, you'll create what's known as a Mobius strip. So again, starting with a flat sheet of rectangular paper, twisting it one time, not twisting the end on one end, but definitely twisting on the opposite end, and then taping the pieces back together will create this Mobius strip. Now, a Mobius strip is unique in that it has no outside and no inside. In effect, it is a surface with only one side. I know that sounds crazy, but if you were to start marking on the strip of paper with a pen and kept going, you would go forever, because it would continue to go around and around and around and around and around, and you would always be marking on the same side, and yet both sides of the paper would be drawn on. It essentially only has one side. Because it only has one side, there's no inner and no outer, or no up and no down, which means that it is not orientable. This is very unlike a curve, which can always be oriented. Let's now take a look at orienting a surface. We're going to start with a smooth surface, or at least something that's piecewise smooth. If it has corners or edges, there's a finite number of them. Let's suppose we take a point, X, Y, Z, on our surface, some smooth part of it. Then we should be able to identify two normal vectors at any point. Let's take a surface and look at the two normal vectors on that surface. So I'm going to start with the hyperbolic paraboloid. If I pick a point on here, let's say I pick this point right here, then one normal vector points out and up in this direction. Another normal vector from the same point points down. That gives me two normal vectors, one in the general upward region and one in the general downward region. This means that I should be able to represent it using the cross product of the directional derivatives, where R is a parameterization of the surface. We found in previous videos that the partial derivative of the parameterization with respect to U crossed with the partial derivative of the parameterization with respect to V gives us a normal vector. It's not necessarily a unit vector though, so to make it a unit vector, we divide by its magnitude, and this will cause it to be a unit vector. Now, if we had parameterized this surface, instead of with R of U and V, instead, if we had written it as a surface F as a function of X and Y, and we parameterized it as x comma y, and then some function of x and y, the easiest parameterization to create, but not always the easiest to work with, then the upward pointing normal vector would be positive, and we'd call that orientation positive. And the unit normal vector would be given by this expression here. The opposite of the partial of f with respect to x in the I hat direction minus the partial of f with respect to y in the j hat direction plus the k hat direction divided by the magnitude of the vector in the numerator. That would give us the partial with respect to x squared plus the partial with respect to y squared plus 1 squared, all underneath a square root. Now, why does this work? So we have two ways of parameterizing the curve. We simply let x be x and y be y, and we write z in terms of x and y. It's a simpler parameterization to create, but not always the simplest to integrate. Then we can also take a surface and we can parameterize it more appropriately. For example, if it is symmetric about a line, then we might use cylindrical coordinates, some version of the polar coordinate system, in order to parameterize it. If it's symmetric about a point, like a sphere or a cone, then we would probably use spherical coordinate system. So we have two ways of parameterizing. How is it that they're the same thing? How is it that r sub u cross r sub v divided by its magnitude is given by this expression here? Let's take a look at this second parameterization where we use x as x, y as y, and we write z in terms of x and y. We're going to treat this as our r, but instead of u and v, we'll just call them x and y. The partial of r with respect to x then would be 1, 0, and whatever the partial of the function f is with respect to x. The partial of r with respect to y would be 0, 1, and the partial of f with respect to y. Then we would do the same process that we did previously when we were looking for a normal vector. We take the cross product of the two vectors. Then we'll find its magnitude. To find the cross product of the two vectors, form the pseudo 3x3 matrix where row 1 is ijk, row 2 is the partial derivative of r with respect to x, 1, 0, partial of f with respect to x, and row 3 is the partial of r with respect to y, 0, 1, partial of f with respect to y. Then evaluate the pseudo determinant of your pseudo 3x3 matrix. Marking out column 1 and row 1, then I have 0 times the partial of f with respect to y, which is 0, minus the partial of f with respect to x times 1. This gives me the negative partial of f with respect to x in the I hat direction. Then we mark out column 2, and because j is in the first row, second column, an odd position, we get a negative multiplied by 1 times the partial of f with respect to y, which gives me negative partial of f with respect to y in the j hat direction. Finally, we mark out column 3, and the 2 by 2 determinant would just be 1. That gives us plus 1 in the k hat direction. Now, this is a normal vector for that parameterization, but it's not a unit normal vector. So we divide by its magnitude in order to get a unit normal vector. In other words, these are identical formulas using different types of parameterizations. Now, you will have to verify after you've found a normal vector that it does in fact point either generally upward if it's a non-closed surface, or out of the closed surface if it is a closed surface. Now, what if it's not? Well, there are two options. For one, you know that the cross product will change signs if you change the order. So instead of r sub u cross r sub v, you could compute R sub v cross R sub u. However, if you've already done the work, to get the opposite normal vector, just multiply through by a -1. That will give you the vector that you want. Let's now take a look at example 1. In example 1, we want to give the upward orientation of the graph of a surface, where the surface is given by lowercase letter f of xy equal to x times y. We want to find the unit normal vector. In order to do this, we're going to start with a normal parameterization. XY doesn't appear to have anything that would lend itself towards either cylindrical or spherical coordinates. So I'm going to stick with the parameterization that X remains X, Y remains Y, and the third component is written in terms of X and Y. So Z equals X times Y. Let's take a look at what the surface looks like on CalcPlot 3D, and then we'll go ahead and compute the formula for the unit normal vector. Here's what the surface looks like. It's kind of a fascinating surface if you think about it. It's sort of a twisted, well, it reminds me of the fighter planes in Star Wars a little bit. So if I'm looking at this surface, I know that if I'm on this part, I want it to point generally in this direction. Now, normal to the surface means normal to the surface, orthogonal or perpendicular. So I know it should point in this direction, not the one that points generally downward. If I'm here, I want it pointing up. And if I'm over here, I want it pointing out this way, which is the generally upward direction, as opposed to pointing down this way, which is generally downward. Let's go ahead and take a look now at our parameterization and the formula. When we look at our parameterization, xy, xy, or x comma y comma xy, we need to find the partial of the function, which is f equal to xy, with respect to x. Well, the partial would simply be y. So in this case, I'm going to get that this is equal to negative y in the I hat direction, which I can write either with I hat, j hat, and k hat, or I can represent in vector form. Then I take the partial of the function with respect to y and multiply it by j hat for the second component, which would likewise give me negative x. Finally, I just take the third component to be the number 1. And then I need to divide this by the magnitude of that vector. This would give me negative y quantity squared plus negative x quantity squared plus 1 squared, which tells me that a normal vector would be negative y comma negative x comma 1 divided by the square root of y squared plus x squared plus 1. Now that I have this, I need to be sure that at a point on the surface that this is actually pointing generally upward. That's our positive orientation. How can I find a point that's on the surface? Well, pick your x and y values and compute the value of z. I believe I chose x to be 1 and y to be 1, so that f of 1 comma 1 turns out to be 1. So the point 1, 1, 1 should be on my surface. If I come to the point 1, 1, 1, and I plot the point and turn it, well, let's turn it a different color so that we can see it, and maybe blow it up larger so it pops out. Then when we look at it, we can see that it is in fact on the surface itself. You can tell when you get it sideways and you can see it on both sides. If you can see the point on both sides, you know it's on the surface. Now I want the vector to point generally up in the direction of the positive z-axis. In this case, we found our vector, which is given by negative y, negative x, comma 1, over y squared plus x squared plus 1 under the radical. Since I'm evaluating this at the point 1, 1, I want to find the normal vector at 1, 1. This would give me negative 1, negative 1, 1 over the square root of 1 squared plus 1 squared plus 1, which would give me negative 1, negative 1, 1, all divided by the square root of 3. Let's see what would happen if I were to plot this vector onto my graph. When you plot the vector, make sure that you use the square root of 3 divided by that inside the vector. CalPlot 3D doesn't like it if you put the factor on the outside. I also widened the vector to a width of 4 and made sure to start it at my initial point on the surface, 1, 1, 1. You can now see when you're looking here that it is pointing generally upward. As we mentioned earlier, since there are some surfaces that are not able to be oriented, it's not possible to define a vector surface integral on all surfaces. This is in contrast to a vector line integral, where it can always be defined. In this case, however, it is something that is very similar to computing the flux of a vector field along a plane curve. We want to do essentially the same steps. Flux was more or less like the net flow rate over a curve, normal to it. To find it, we chopped the curve into tiny pieces, chose a point in each piece, computed the dot product between the vector field F and the normal vector to that piece, and then added them all together for all of the pieces and took the limit as the length of each piece went to 0. We want to do the same thing here, but instead of to a curve, we're going to do this to a surface. We're going to chop our surface into tiny little pieces of area. We're going to choose a point on each tiny piece of area and compute the dot product of the vector field with the normal vector to that piece of area. We're going to have to compute the normal vector at a point on that tiny piece. And then once we've found all of F dot ends for all the little pieces on the surface, we're going to add them together and take the limit as the area of each piece goes to 0. Now, theoretically, it does not matter what shape the tiny little piece of area has, whether it's a disc like a circle, whether it's a rectangle or a square or even a trapezoid. That's in theory, however. In practice, it is very difficult to compute without having a regular geometric shape. What we're going to do is use the same parallelogram spanned by the directional derivatives to approximate the area of that piece. These parallelograms, recall, are actually a piece of the tangent plane to the surface at the particular point where you calculated the normal vector. Now, when we had a density function, the surface integral of the scalar valued function could give us the mass of the surface, how many kilograms it had. So what then does the surface integral of a vector field represent? Let's suppose that our vector field is the velocity field for some fluid. This fluid flows through the surface, not inhibited by the surface at all. So it's flowing through it, permeating the surface. If the density of the fluid, and again we have the density, rho of XYZ, then we can call the mass flux of the fluid as the rate of mass, kilograms, per unit area across the surface, measured in mass per unit time per unit area, like kilograms per minute per square foot. The rate of flow will be the density times the normal vector, measured in mass per unit time per unit area. The component of the vector rho times the vector field v in the direction of the normal vector of the surface at point P is rho v dot n. To approximate the mass of the fluid per unit time flowing across a tiny portion of the surface, multiply rho v dot n at that point P by the area of that small piece, S sub ij. And we'll sum up these values for all the pieces of the surface and take the limit of the Riemann sum. Let's take a look at a picture which will make it a little bit more clear while we put up the formula as well. To compute mass flux across a surface S, we're going to divide the surface by cutting it into small pieces. Ours are going to be small parallelograms spanned by the directional derivatives. We can say that we're cutting it into m pieces in one direction and n pieces in the other direction. Then we get a tiny little portion shown on the image on the right with S sub ij showing up as a curved rectangle. When we look at that curved rectangle, we have a normal vector which points orthogonal to the surface coming directly off at the point where we evaluated the normal vector. We also have, however, the vector field itself, which is the velocity of the fluid, given by F equal to V for the vector field. We want to know what portion of the vector field lines up with the normal vector, which is causing it to flow through the surface S. In this case, we can define the surface integral over S as rho times the vector field dotted with the unit normal vector with the surface integral differential. And this, of course, is the limit of a double Riemann sum. This is what we mean by a surface integral on a vector field. If we allow the vector field rho times v to be just some arbitrary vector field f, it leads to the following definition for the surface integral of a vector field over a surface S. We start with a continuous vector field with a domain that contains the oriented surface S with unit normal vector n. Now, of course, the unit normal vector n will be different at different points. The surface integral of the vector field over the surface, which is sometimes called the flux of F across S, or the flux integral over S, is given by the surface integral of F dot the surface integral differential, ds with a vector over it. This is the same as F dot the unit normal vector with, again, the surface integral differential, but without the vector on it. Note that ds with the bar over it is equal to the normal vector times the surface differential. Let's go ahead and suppose that the surface is given by some function, lowercase letter f, of x and y. The vector field, uppercase letter f, is given in terms of its components, p, q, and r, such that the vector field, uppercase letter f, is p, q, r. And we want to have the upward orientation. In that case, we can rewrite the surface integral of a vector field by writing p in the I direction, q in the j direction, r in the k direction, dotted with the unit normal vector, which we saw earlier could either be r sub u cross r sub v divided by its magnitude, or this opposite of the partial of f with respect to x, I hat, minus the partial of f with respect to y j hat plus k hat divided by its magnitude. Now, the surface differential ds without the vector over it is equivalent to the magnitude of the normal vector with the area differential. This is converting it into a double integral. And the double integral is evaluated on the parameter domain defined by u and v, or in this case, x and y. Notice, however, that this causes the magnitudes of the unit normal vector to drop out, or not the unit normal vector, but the normal vector, the magnitude of the normal vector to drop out. When that happens, we can get a dot product between P, Q, R, and the opposite of F with respect to X, opposite of F with respect to Y, K, which gives us a formula on a double integral over the parameter domain of negative P partial of F with respect to X minus Q partial of F with respect to Y plus R with the area differential. This caused that square root to drop out, which is a very happy moment. Now, of course, this may not be the orientation that you want. You may need to multiply through by a -1, in which case you would get the double integral you see here. Always plot the surface to verify that the normal vector points generally upward for a general surface, one that's not necessarily closed, or if you have a closed surface, make sure that it's pointing out, right? Out would be away from the solid object, right? And that will be the positive direction for a closed surface. Now, this is only written for surfaces that have been parameterized in terms of x and y. So x, y, and then z in terms of x and y. We could have parameterized it differently. It is possible on surfaces to parameterize with y as a function of x and z. If you parameterize y as a function of x and z, you're going to get a different formula, namely the one you see in the last two rows here. This is a parameterization where we've solved it for y instead of for z. So in our parameterization, we would have had out here to the side, and let me make note of this. This is where we're parameterizing. And we have the parameterization y as a function of x and z, which is equal to x, f of xz, and z. In that case, it changes the formula so that the +1 goes on j hat, and it's the other two that have the negative. This results in the formula that you see for the double integral, the opposite of the partial with respect to x times p plus q minus r times the partial of f with respect to z. You could also have parameterized it in terms of x. If you'd parameterized it in terms of x, you would have gotten the first two lines where x is a function of y and z. Then your parameterization, r of x and y, could be given by f of y and z, comma, y, comma, z. And in this case, you're going to get the +1 on I hat, since that's the one that you have written it in terms of x equals. And that will change your formula on the double integral over the parameter domain D to be P minus Q times the partial of f with respect to y minus r times the partial of f with respect to z. This gives you three different formulas. One solved for z equals, one solved for y equals, and one solved for x equals. Given that you have to verify that the normal vector points in the correct direction and that you may need to multiply by a -1, there are actually 6 possible forms that you may need to look at. If we thought of this surface, z equals to some function of x and y, instead as g, a function of 3 variables, x, y, and z, and we wrote it as z minus f of x, y, then we could represent the notation, the square root of the partial of f with respect to x quantity squared, plus the partial of f with respect to y quantity squared plus 1, as the magnitude of the gradient of g, del g. We could use this notation to substitute for the magnitude of the normal vector, since it shows up twice in our integral, and use it to cancel out rather than having to write that entire process. In fact, you don't actually need the magnitude of the normal vector because it's going to cancel out of the integral. And since it cancels out of the integral, then you can actually represent it without it. We could also have represented the parameterization as r a function of u and v, where u is not x and v is not y. This would lend itself to parameterizations done in terms of cylindrical or spherical coordinates. When we do that, then it becomes the vector field f dotted with the normal vector, which is r sub u cross r sub v divided by its magnitude to get a unit normal, multiplied by the surface area differential, which is the magnitude of the normal vector times the differential dA. Again, the magnitude will drop out, and you see that you get something very similar to what you got previously with vector line integrals. You have the vector field parameterized as a function of r of u and v, dotted with a normal vector, r sub u cross r sub v, in a double integral over the parameter domain. Again, note that you must check the orientation of the normal vector. If it's not pointing generally up or out of the shape, simply multiply through by a -1, and that will fix it. Let's now take a look at example 2. In example 2, we want to calculate the surface integral f dot ds, where ds is the surface integral differential with the vector over s, where our vector field is given by 0, -z, y, and the surface over which we want to evaluate the vector field is a portion of the unit sphere in octant 1 with outward orientation. Now let's think about what outward orientation means, and then think about what it means for this part of the sphere in octant 1. So let's consider a sphere. It's a closed surface completely enclosing the solid ball, which means that the normal vector points out of the ball. In this case, this would be the normal vector. Now let's suppose that we only want to consider the part in octant 1. If we're looking at the part in octant 1, remember positive y is this way, positive x this way, positive z this way. So this region here is octant 1. That would be this portion that you see right here, which is 1/4 of the sphere, or rather 1/8 of the sphere. To point out, then, means generally pointing in this direction, where again, the normal vector is generally pointing upward, above the XY plane. Now, it is possible in this case to parameterize with spherical coordinates, because it will be symmetric about a point, namely the origin. Or we could use the parameterization x, y, f of xy, Whichever way you choose to go, what you want to do first is to find a normal vector. When we do this, I chose to go ahead and let my parameterization be the rectangular one, where I chose X to be the first parameter, Y to be the second parameter, and I wrote Z in terms of X and Y for the third parameter or third component. When I'm looking at these, how did I get the equation Z equals square root of 1 minus X squared minus Y squared? Well, a sphere is given by the equation X squared plus Y squared plus Z squared equal 1. But I know that when I'm looking at this 1/8 of a sphere, the portion in octant 1, that Z is always positive. In fact, X is always positive and Y is always positive as well. But basically Z is positive. In this parameterization, X is the first parameter, Y is the second parameter. The third component has to be Z equals something in terms of X and Y. So I solve the equation for Z, which gives me plus or minus the square root, but it's strictly above in octant 1. So I use the positive radical of 1 minus X squared minus Y squared. I could also have parameterized in the spherical coordinate system. In this case, we know that the radius of the sphere is 1. So I would set rho to be 1. And I would have sine phi cosine theta for my X coordinate. That's R cosine theta. And I would have R sine theta, or 1 times sine phi sine theta for my second component, and 1 cosine phi for my Z component. In this case, rho is constant because I'm on the surface of a sphere, the part of the sphere in octant 1. However, theta, to stay in this quadrant right here, theta has to rotate from 0 to pi over 2. And phi has to rotate from 0 here down into the xy plane where it is pi over 2. You could use either parameterization, whichever one seems the most suitable to you. In my case, I chose to go ahead and stick with a straightforward parameterization. What we want to do now is we want to compute using the formula. So I'm going to need to compute the partial of f with respect to x, the partial of f with respect to y, and put them into the double integral over the parameter domain, the restrictions on x and y, where I have negative p times the partial of f with respect to x, minus q times the partial of f with respect to y, plus r as the integrand. Go ahead and pause the video to work out this part, then turn it back on, and we'll continue our work. Recall that we have defined our surface as a function of x and y, the square root of 1 minus x squared minus y squared. When I take the partial with respect to x, I get 1 over 2 the radical times the derivative of the inside with respect to x, which is negative 2x. The 2's cancel, giving me negative x divided by that radical. Similarly, I would get the partial with respect to y to be negative y divided by that radical. Now I need to go ahead and find the vector field components p, q, and r, but in terms of x and y, my two parameters. P is 0, q is negative z, but z is this radical. So q becomes negative the square root of 1 minus x squared minus y squared. The third component, r, is given by y. The next thing I want to do is to put it into the formula to find the vector field surface integral, or the surface integral on the vector field. In this case, p was 0, so negative p times the partial of f with respect to x is going to drop out. Negative q times the partial of f with respect to y being subtracted gives me two double negatives here, making it plus. the radical times negative y divided by the radical. The radicals will cancel, but I've got 3 negatives, which is going to give me negative y. Then I add r. R was just y, so I get negative y plus y, but that gives me 0. In other words, the vector field gives me 0. The net flow through the surface of that 1/8 of a sphere is 0. It doesn't mean there's no flow. It simply means that the amount coming in is the amount coming out. Now, we should verify that our vector does indeed point in the general upward direction. It won't really affect our result since it came out to be 0, but it is a good habit to verify. When we're thinking about this quarter circle out here, there are various points we could use. We could use 1, 0, 0. We could use 0, 1, 0, or we could use 0, 0, 1. Of course, there are infinitely many points, but those are the 3 that are the easiest to compute. I chose to compute 0, 0, 1. Let's go ahead and compute the normal vector at that point and ensure that it points outward. Do you remember what the normal vector in this case turned out to be? The normal vector, again, is given by the representation that you see here. This is the normal vector that's in the numerator. It's not the unit normal unless you divide by its magnitude, but it is the normal vector. The opposite of the partial with respect to x in the I hat direction minus the partial with respect to y in the j hat direction plus 1 k hat. Go ahead and compute that normal vector at the point 0, 0, 1 and see if when you plot it on that part of the sphere, it does point outward. Then turn the video back on and we'll work it together. In order to find the normal vector, you can either use a normal vector, which is simply the numerator, or the unit normal vector, the unit vector. It doesn't matter which one you use, they'll point in the same direction, just with different magnitudes. If you use the unit normal vector, you can use the notation magnitude of del G to represent the magnitude of the normal vector without having to write it out by hand. In this case, we found the partial with respect to x to be negative x divided by the square root of 1 minus x squared minus y squared. So I should have a double negative up here. And then we found the negative partial with respect to y to be another double negative, so it would be positive. In this case, when we substitute in the value that x is 0 and y is 0, both the first and second component of the unit normal vector zero out. The third component is a constant 1. Evaluating the magnitude gives us 0 squared plus 0 squared plus 1 squared, which gives us k hat, which is the unit normal vector pointing straight up in the normal direction. Let's take a look now at what it looks like. Here's an image of the surface and the vector field. The point we evaluated the normal vector at is right here on the positive z-axis at 0, 0, 1. K hat points directly up, which does verify that the normal vector we found does point in the upward or outward direction. So it is correct. Can you tell by looking at this surface why it is that we got the flux of the surface integral to be 0? Here it is in CalcPlot 3D. If you're looking at it from a different orientation, why do you suppose that we got no flow through the surface normal to the surface? If you look at the vector field, you can see that the vector field is flowing along the surface in the direction of the surface, tangent to the surface. There is no portion of the vector field that is flowing normal to the surface. And this is why we got 0. Let's take a look at our last example, example 3. In this case, we're given a vector field in 3 dimensions, x squared plus y squared, comma z, comma 4y, in meters per second, representing a velocity field of a fluid with a constant density of 100 kilograms per cubic meter. We want to let the surface be the half cylinder given by a parameterization, this time in terms of u and v, where the first component is cosine u, second component is sine u, and third component is v. Now u is going to vary from 0 to pi so that we get a half circle, a semicircle in the xy plane. V is going to vary from 0 to 2, which is going to pull the image of the semicircle up so that it has height from 0 to 2, giving us half of a cylinder. We want to calculate the mass flux of the fluid across this surface. In order to do this, because it is parameterized not as x comma y comma f of x and y, but instead in terms of r of u and v, we will want to use the other form of the flux integral, which is the vector field parameterized by r of u and v, dotted with a normal vector, r sub u cross r sub v, evaluated in a double integral over the parameter domain, where u varies from 0 to pi and v varies from 0 to 2. You will need to first substitute the parameterization into the definition of the vector field. Cosine of u will replace x, sine of u will replace y, v will replace z. Then you will need to compute the partial derivative of this parameterization with respect to u and the partial of that parameterization with respect to v, find a normal vector by crossing them together, then taking the dot product of the vector field at the parameterization with the normal vector. Then finally evaluate over your parameter domain. In our case, our vector field is not just given by v, but by rho v, where rho represents our constant density of 100 kilograms per meter cubed. Go ahead and pause the video to work this one out, then turn the video back on and we'll work it together. So in this case, I multiplied the density, 100 kilograms per meter cubed, by the dot product of the vector field parameterized using our parameterization with the normal vector, r sub u cross r sub v. In this case, when I do the dot product, I get cosine u plus v sine u plus 0. When I multiply this by 100, I will come up with the integrand for my vector surface integral. When I evaluate this, I do it between u from 0 to pi and v from 0 to 2. When we're looking at this particular one, note that we've got 100 times sine u minus v cosine u as the integrand. Before we go any further, we should verify that this normal vector is pointing out of the half cylinder. Let's think about a point that would be on this half cylinder. If I let u perhaps be 0, and I then consider v to be 0, then I would have the vector 0, 0, 0, which is not going to help me. Instead, let's go ahead and evaluate it at some different point. Where is our vector not going to be a zero vector? In this case, when I look at it, let's suppose that I let u be pi. If I let u be pi, then I get -1, 0, 0. Let's go ahead and figure out what value this corresponds to on our surface. Let's go ahead and look at the point that we're going to have on our surface. This is a picture of the surface in CalPlot 3D in the vector field. You can see that we have a half cylinder right here going from z equals 0 to z equal 2. It is defined for theta between 0 and pi, or u in this case, between 0 and pi. If we take this and we rotate it, we can see that it is graphed only where y is non-negative. That means that we're in octants 1 and 2, which is where, of course, u would vary from 0 to pi. We've got a vector of -1, 0, 0 corresponding to what point on our particular graph. If we look here, we can allow v to be any value that we want, and we can choose u, in this case, to be pi. Cosine pi is -1, sine pi is 0. So for any value of v, we've got an edge from -1, 0 to any value between 0 and 2 on the z-axis. When we look at our graph, -1 will be on the x-axis, and let's rotate it around so that we get the x going perhaps in the direction we're accustomed to seeing it. Now we have -x off to the left and +x to the right. So we come out here to this corner. We don't move into the page or out of the page, so y is 0, but I can move up or down along this edge. All points along this edge are going to have the value cosine u, sine u, v, where u is pi. Now, which way did my vector point at that particular spot? Let's suppose we take the point here at -1, 0, 2. Let's go ahead and plot that point now. When we plot the point, we have -1, 0, and 2. Or let's do 1, -1, 0, and 1. And I'll make it bright blue and larger so that it will stand out. There it is right there along this edge, as I pointed out before. Now, the normal vector I got at this point is -1, 0, 0. So now let's plot a vector starting at the point -1, 0, 1. So we'll enter our initial point as -1, 0, 1. And we'll have our vector of -1, 0, 0. Is it pointing out of the solid? All right, let's make this one, what would be a good color? Let's make it pink, and we'll make it thick so it really stands out. There it is. Is it pointing outside of this half cylinder? And the answer is yes, it is pointing outside of the half cylinder. You can see the point right there, and it is definitely pointing out of the shape, not towards the interior of the shape. So the normal vector we have found is the effective one to use. Now that we've determined it is the effective one to use, we can set up our integration with that integrand, and we can integrate either with respect to u or with respect to v first, because on the parameter domain, it is rectangular. I chose to integrate with respect to u first, just to get the harder part over with. The integral of cosine u gives me sine of u, and the integral of v sine u gives me negative v cosine u, where v is simply a constant as far as u is concerned. Then I evaluate between u equals 0 and pi, leaving the 100 on the outside as a constant factor. Sine of pi minus sine of 0, they're both 0, so the difference is 0. Then I factor out the negative v. I find cosine pi minus cosine 0 is -1 minus 1, or -2, multiplied by the negative v. Once I have that, I multiply the -2 by negative v to get 2v, multiplied by 100 gives me 200v dv. This then, when I integrate, gives me v squared divided by 2. 200 divided by 2 gives me 100 v squared to evaluate from 0 to 2. 2 squared is 4, 0 squared is 0. So I get 400 kilograms per second per square meter of area. This is the mass flux across this surface. Now, what if I wanted the flow rate instead of the mass flux? Mass flux is measured in mass flow kilograms per unit time per minute per unit area per meter squared. However, what if I just want the flow rate, which is the volume per unit of time? To get volume per unit of time, I leave out the density function, and I simply include the flux integral v dot a unit normal vector on the surface integral. In that case, the last one would take out the 100 kilograms per meter cubed, and I would get 4 meters cubed per second. That would be the flow rate of the vector field across the surface with the volume of flow per unit of time. Remember that mass flux measures how much mass is flowing across the surface or through the surface. Flow rate measures the volume of fluid flowing across or through the surface in the direction of the normal vector. Believe it or not, we have finally reached the end of section 6.6. I truly believe this section should have been split into at least 2 sections. It is a lot of information and a lot to cover. You'll be happy to know that the remaining 2 sections of the textbook in chapter 6 are much shorter. It may be that your multivariable calculus class ends with a discussion of surface integrals. If you have time, though, you really should check out the next 2 videos, which tend to tie together everything we've learned in chapter 6. In 6.7, we'll look at Stokes' theorem, and in 6.8, the divergence theorem. These pull what we learned about the fundamental theorem of calculus into higher dimensions. I hope to see you soon for the last 2 videos in multivariable calculus.